done a wonderful job of sending the news out. So today I'll be mostly introducing Vias and have some talk about what we do and all, and then will carry on with the technical presentation. Will Mars, he is the founder and president of Endurica, and he is a leader in the solutions of intersection of engineering, elastomers, and durability. So he's the author of Endurica Fatigue Solver, which is actually used in the Dassault System software product FE-Safe rubber. His software solution is available through Dassault System, and also it can be independently purchased. And he has received several awards for scientific contributions and innovations, including 2007 Sparks Thomas Award for ACS Rubber Division, and is an editor of the Journal of Rubber Chemistry and Technology, and also a past editor of Tire Science and Technology. So his contributions span a topic range including material characterization, product evaluation, finite element modeling, fracture mechanics, and fatigue life prediction methods. He has more than 25 years of experience in the rubber industry, and he's also very well known for his fatigue solution. He earned his honors BA in mechanical engineering with polymer specialization from University of Akron, and his MS and PhDs at the University of Toledo. For me, I received my PhD from University of Iowa. I worked on fracture mechanics problems with probabilistic analysis, and then I have been mostly involved with solid mechanics stress analysis, fatigue and fracture, stochastic modeling, and all. I used to work at Structural Integrity San Jose for their consultant for nuclear industry, nuclear and fossil. And then I have experience in the oil and gas industry for last almost 5 years. I'm involved with fitness for service kind of work, optimization and reliability, material degradation evaluation, and also any sort of nonlinear FE analysis. And I'm also involved with ASME codes, and I'm a member of Material and Fabrication Committee at ASME, and try to get myself involved with the new techniques and technologies that are coming in and how it can help the industry moving forward. So with that, I would like to quickly introduce our company Vias. So today the webinar is jointly hosted by Vias and Endurica, and we'll show an example problem where we actually worked together on the finite element side and also the fatigue analysis part of it together. So I'll let Will present that one at the end of his technical presentation on Endurica. We have a cross industry experience, so we have experts who have many different industry experience like aerospace, automotive, oil and gas, and in general energy industries like nuclear and fossil. Our main office is in Houston. We are mostly Houston based with the training centers here. We also do provide training apart from software services and consultancy. We have presence in other U.S. locations such as Chicago, Cincinnati, Detroit, and in the Bay Area, San Francisco. We are a Dassault System Simulia partners. We do work with their software solutions, Abacus, iSight, FE-Safe, and Tosca. So FE-Safe is the one where Endurica is. You can, as part of that FE-Safe extension, you can buy Endurica. We provide virtual design experiments through collaboration and data analytics. So we are into automation of your workflow and also data analytics solution. And we also started looking into the 3D printing and simulation for additive manufacturing. Will, can you go to the next slide? Yes, thank you. So our capabilities are mostly around simulation consulting services. So we have strong expertise in FEN and CFD, fracture mechanics and damage, and also composites and elastomer reliability-based design, multi-physics simulation. It can be fluid structure interaction or soil structure or mechanical or structural acoustic vibration, those kind of thing. And also, as I mentioned, we also venture into the data analytics applications for the engineering industry. So, yeah.
All right.
So having that's kind of like overall introduction for Vias. I would let Will carry on from here on his Endurica solutions, and then he will talk about the technology behind Endurica, the theory behind Endurica as well, and then at the end we have an example problem where it's kind of taken from a real life project, but of course we cannot show the details of that, so we made up some of the geometries and all the applications, and then but it will show you the value of using the solution for fatigue durability for rubbers. Thank you, Will. If you can take from here.
Yep, thank you, Arundham. Really glad to be here. Really glad to have this chance to
Hello.
tell you about what we're doing with.
Will, you might
Yep.
have to unmute.
Am I muted? Hold on. My microphone says that I am not unmuted.
Yeah, I can hear it. It was from my end. Thank you. Yeah.
Okay. Thank you for the introduction. Glad to be here. I'm going to start off with a really high-level slide, just to talk about the kinds of solutions. Of course, Endurica, we've been around since 2008. We are famous for and focused on durability and elastomers. That's all we do. We're part of our solution, as Arundham mentioned, is software. Right, we have software solutions that allow you to take your fine element model, model your part operating under whatever your duty cycle is, and then to learn about the fatigue performance, to go back into that analysis and kind of diagnose where damage is coming from, the causes of damage. Very quickly learn how to get durability right. That's really what we're all about. In addition to software, Endurica also has developed solutions for characterizing materials, right? If you're going to run a simulation, there's some things you need to know about your material. We have a service that we've developed, fatigue property mapping. You can send us samples of your material, and we can get them tested and curve fitted and derive all the parameters that it takes to feed a durability simulation. So that's offered as a service, right? Send us material, we'll send you material properties. And then we also have another set of solutions where we have some customers who would prefer, rather than characterizing materials as a service that we provide, they would rather do that in their own lab. So people who are looking at hundreds of compounds a year, or people who want to be very in control of lab priority and confidentiality and that sort of thing. We actually sell testing instruments that implement our measurement procedures, and you can buy these, you can put them in your own lab, you can use our methods. What comes out of these instruments is basically ready out of the box to feed FB-safe rubber, to feed Endurica CL software calculations. So from end to end, measuring materials all the way down to fatigue life prediction, we've got you covered. We've got everything you need. All right. So in the next 40 minutes, I'm gonna go pretty fast. The first chunk of material I'm going to present to you is really an update. I'm gonna assume that you know a little bit about our solutions, and what I'm really going to talk about is what's new. We've really been developing we've continued to develop the technology, and in the last year there have been a number of really I think exciting developments in all of the solutions. So I'm just going to kind of just do a quick scan through what those developments are and how they can benefit you. I'm also going to spend a few minutes talking about user validation experiences. We've had a number of customers who've started to talk publicly in conferences and that sort of thing about what they're doing with our software. So I'm going to I won't go, again, not not time for much detail, but I do want to just kind of make mention and give you a reference you can follow up if you're interested. But this is a solution that people are using to solve real tough durability problems, and then finally I'll talk about some future directions. And then after this set of slides, then we'll go in and we'll talk about a specific example, this mud piston seal, mud pump piston seal analysis that we've done. All right. So this is a I mentioned that we have a fatigue property mapping service. This is how we measure the properties that go into the analysis, and that service has a number of different experimental modules. This is a list of all the modules, they cover the basic things like measuring stress strain curves. That's the hyperelastic module. Basic things like measuring a crack growth rate curve, your crack precursor size. That's our core fatigue module. And then the other modules are really what I call special effects, right? In rubber fatigue problems, depending on your application, depending on, is this high pressure, high temperature, or are you using natural rubber that strain crystallizes, or there's all sorts of different applications where there are what I call special effects. And in order to properly do a durability analysis, you have to account for these special effects. So anyhow, so this is our list of experiments that we can do. If you go to our website, we actually give a lot more details on all of these. The one that I've highlighted in red, this is a brand new experiment that we've developed in the past year called the CREEP module. And I'm going to spend a little bit of time just, again, this is a what's new talk, so I'm going to talk less about what's already there. I'm going to talk more about what's new. So this new CREEP crack growth module is an experiment that we developed in partnership with Schlumberger. This is work that is published in the ECCMR proceedings coming up in Munich, Germany. And the purpose of this experiment, sometimes in applications where you have very large loads that are applied over a very long time, the crack growth rate behavior of the rubber can become not only cycle dependent but also time dependent, because of the fact that a crack can grow very slowly in rubber as a function of time. So what you're looking at on the left-hand side, these are actually images of a crack that were taken. This was for I believe it was an HNBR compound, but these are images of a crack that's just being held statically open, and due to CREEP crack growth over time, you can see I've marked out the time scale here. You can see the crack growing as a function of time. We can take this information and reduce it to what I call a CREEP crack growth rate curve. And the Endurica software, the FE-Safe rubber software, if you give it the CREEP crack growth rate curve and the traditional fatigue crack growth rate curve, what it can do is it will use this rule that I'm showing in the bottom right to come up with a combined, you call it combined CREEP fatigue crack growth rate, but it's the cycle dependent crack growth rate plus the time dependent crack growth rate, accounting for the period of each cycle, right? So the model knows how to deal with this time dependence. The crack growth rate plot that I'm showing you on the upper right here, this is a set of sort of computed, like I say, combined CREEP fatigue type curves, and you can see that the predicted curve actually depends on the period of the cycle. So if you have very, very rapid cycling, there's not enough time for much creep to happen, and so at a given energy release rate, you have lower crack growth rates. That's the solid line. Versus if you cycle on a much slower time scale, say 10 seconds, then the rate of crack growth per cycle actually goes way up because of the fact that that creep crack growth is part of this. And this phenomenon, again, it's important in problems where you have high loads that are present for long periods of time, and as you might in downhole applications where you have very high pressures, high temperatures. You're leaving a seal in place for, you know, the life of the well. So anyhow, so this is a new experiment we can measure, and then these parameters again go right into the code. So that's what's new on the experimental side. Now I'm going to switch gears and talk a little bit about some new things in our fatigue solvers. So as you may know, we actually have two fatigue solvers. Both of them kind of originated from our original code, Endurica 1.0. And when we first developed FE-safe rubber, there was kind of a branch internally to the code. And the codes took sort of two development paths. You know, FE-safe rubber is the solution that integrates with the Dassault FE-safe application, right? It's a plug-in to FE-safe. And then Endurica CL is our standalone code that you can use, you know, kind of on its own and it's I guess what it's maybe famous for is A, being standalone, and B, being code neutral. So it can talk to Abacus, it can talk to ANSYS, you know, other finite element codes. One thing that we've done in the last year is we've re-architected the internals of the code so that now when we build these solutions, they're built off of the same code base again. And this is all internal, so people say, well, why do I care? But it's really been a major kind of restructuring of the internals. It's cleaned up a lot of loose ends. And what it means for you as you know, people who are using the solution, it means that in the future there's going to be faster migration of capabilities. You know, a feature that shows up in one piece of code really is much easier to transport across. So you'll see the you know, the differences in capabilities between the two codes will be evolving, you know, together, and more code reuse. So there's you know, we've more you know, fewer lines of when we reuse code, it you know, fewer opportunities for bugs, easier to find bugs, and so I think you're going to find that the code has a much higher quality than earlier versions now that we've finished this merge. As part of this internal re-architecting, we have greatly expanded our set of QA benchmarks, and we're currently up to 75 different analysis cases. So if you think of, and these cases that we benchmark against are from all sorts of different things: automotive, oil and gas models. You know, the one brag I like to make is that we have solved more rubber fatigue problems than I think most people know that exists. You know, think of 75 different ways that rubber can break, and we're anyhow. So we've got a very large set of QA benchmarks that test all the features of the codes in lots of different ways. So you know, again, just real improvement to the architecture that is present with, and that's available through FE-safe Rubber 2017 and Endurica 2.5. All right, one of the so one of the features that was in Endurica 2. You know, that was in earlier versions of Endurica, but that hadn't made it over to FE-safe Rubber yet, was what I call equal area discretization. Now, when Endurica does a fatigue calculation, we use a technology known as critical plane analysis. And basically what this means is that we are testing we're testing the fatigue life of cracks in all sorts of different orientations. And in the original version of the code, the way we organized that search was by using this topmost half sphere, right? And notice how the sphere is discretized with a rectangular grid. It's kind of an obvious way to do it, right? Spherical coordinate system. The trouble with this old spherical grid is that if you look at the size of each domain, each facet on the sphere, the search is very finely discretized at the pole of the sphere and very coarsely discretized at the equator. And what this meant was that you always sort of kind of had this weird mixture of accuracy versus computation speed, and in some orientations it was fast, in other orientations it was coarse. So it was just kind of a weird lopsided way to do the critical plane search. And so what we've done now, and this is now propagated into FE-safe rubber, is we're using equal area discretization. And so this set of meshes in the bottom row, these are all examples of equal area discretizations of a half sphere. This one on the left, that is the coarsest possible discretization. It's just a tetrahedron. Of course, it runs very fast, but we normally would run more planes than that. But and as you go up, you can see that the key property here is that every facet of the discretization has exactly the same area. So now when we do the critical plane search, it's not as if one plane counts more than the other. They're all kind of on an equal footing. And what this means is that you can actually get to the same level of accuracy using a coarser overall discretization. So very, very, very convenient, very powerful. It's in a way it's invisible to you unless you go plot results. You don't have to do anything to access this really. But just to give you an idea of what this buys you, this is a plot of compute time and computed fatigue life for a benchmark case as a function of mesh density with the new case. And the bottom line is that if you ran this with the original discretization, the runtime was about 5 seconds. And with the new runtime at the default of nmesh equals 5, we had a runtime of about 1.5 seconds. So it's a speed up of nearly a factor of 3, really, for the same level of accuracy. All right, another new feature with the Endurica 2.5 and FE-safe Rubber 2017. This is, by the way, this is a feature that's available in both. There's a new tool for visualizing the results of the critical plane search, right? So at a point in your final model, after we've analyzed all of the different possible planes on which a crack could initiate, we can plot the fatigue life as a function of crack orientation on the sphere, and we've now given you a tool that you can use to do that. This is a screenshot from that tool. So this sphere represents all of the possible crack orientations, and we've marked the most critical plane with this vector here. You see this black arrow that's marking the critical plane for this particular load case. This is a useful feature when you want to understand the relationship between the loads on your part and their directionality and the damage that's accumulating, right? Right, so that's a new feature. Probably the most important new feature in FESafe Rubber 2017 is support for multi-block loading. Now they've had this for metals for a long time, but our plugin did not fully support this until recently. And what this feature allows you to do is to set up multiple load cases. For example, this is an automotive CV boot cover, CV joint cover boot, right? So there's a joint in here that flexes, and when you flex it, this boot bends, and then this thing rotates, and we want to protect that joint. And in this is a very simple case where we just have two load cases. In one case, the load case is a 5-degree, right? It's rotation with a 5-degree bend in the joint. In the other case, load case 2, it's a 30-degree. It's one rotation with a 30-degree bend in the joint. And this new feature allows you to set up problems that have a form like, well, hey, I want to know how many repeats of the following schedule of loads the part can endure. So here I can specify I've got 1,000 repeats of load case 1. I've got 3 repeats of load case 2. How many times can I repeat that schedule before the part breaks? And I've here to keep things simple, I've just put 2, but you can have as many as you like. If you have if you have 20 different load cases and you want to set them up and model them all, then FESafe Rubber can combine those and give you results based on the entire schedule of load. So it's a very powerful feature, a very convenient feature, and I think it'll allow people to solve really complicated fatigue problems. All right, this is a feature that's aimed at people who are modeling tires, and this is a feature that, by the way, is currently only available in Endurica CL. But if you have a tire, and you want to model rolling of the tire, you don't necessarily have to model actual physical, Lagrangian rolling of the tire. You can simply use a modeling procedure called steady state rolling, and Endurica knows how to recognize the results from a steady state rolling analysis. And so what it will do is if you say this is a rolling model, Endurica will recognize that your goal is to compute a fatigue life for each element on a tire cross section, right? So even though this is a 3D model, it reports the results on a 2D cross section, and the time histories for each element are derived by following the strain history as an element travels around the tire. So again, this is for rolling structures. If you're doing tires, if you're doing a roller, then this would be a feature that would be interesting for you. Another feature that's new with Endurica CL is we have outputs that allow you to ask for cavitation, wrinkling, and crack open close state information. So the cavitate, sometimes in rubber, depending on your loads, you can actually have failures that are not necessarily due to fatigue. For example, if you put a high hydrostatic tension on the rubber, where the hydrostatic pressure gets bigger than 5/6 of the Young's modulus, voids will spontaneously open up in the rubber, and that can be a failure mode. Endurica knows how to check for this, and if you ask for it, it'll give you a time history of where and when cavitation might be happening. Similarly with wrinkling, this happens on free surfaces where you have compression. We're using the criterion that was published by Gent and Choi back in the late 90s to check for surface wrinkling and give you kind of flags when that might be happening. Finally, there's an output request that can tell you the open close state on a crack, right? As we're doing a critical plane search, Endurica knows the time history of basically every crack and every orientation. And if you want to know when the crack is open or closed, you can say, hey, tell me that. And it'll give you a time history of that of what the crack state is. Here's an example of that for a tire model. This is right. So here's a tire model. This is a rolling under a straight ahead rolling under a load, and the blue line represents think of this as the energy release rate on the crack as it goes through one revolution of the tire. The center of the footprint of the tire is 0 degrees. You can see when we're at the top of the tire, far away from the footprint, there's a small amount of load. That's probably due to the inflation pressure of the tire. As we approach the footprint of the tire, there's some bending, right? You're taking a round structure and you're applying some bending to flatten the structure out through the footprint. That causes the loads at the belt ending to experience a spike. As it enters the footprint, goes through the footprint. On the other side of the footprint, as that bending is reversed, that crack that opens on one side of the footprint actually becomes completely closed. And you can see that by looking at, I've taken the crack state output from Endurica and I've plotted that as this gray bar. So you can see most of the time this crack is open, but there's an instant on the exit of the footprint where that crack closes. And of course, when a crack closes, then you have no, a closed crack doesn't grow unless you're shearing it, and so we account for that, crack closure effect. This is an image of the results of the critical plane search for this tire analysis. The failure mode was predicted as the belt ending. And this is just a plot of the red planes are the planes that get the most damage. The blue are the planes that have the least damage. So that's a little bit about updates to software things. I'm going to switch topics now and review some things that customers have been doing with our solutions. This is a characterization that we published with ExxonMobil, looking at applying our solutions to TPEs, right? The defining feature of TPEs is they show a lot of plasticity. And if you go back and read this paper, you can kind of see how we've handled the plasticity. So a lot of times people ask us, can you use your methods with TPE materials? And the answer is yes, but you do have to account for the inelasticity, and our solutions allow you to do that. So you can, like I say, read more. This has just come out in the next issue of Rubber Chem and Tech. Another interesting example is looking at very complex load histories. Right, in the automotive sector, it's pretty common to have road loads. This is 3 channels going into a bushing in this case, and so this is a work that we did with GM, where we did fatigue analysis, and we were able to predict the failure modes and life based on very long, complicated load histories. Another example. This was a really nice example that Tenneco did using our software, and they actually went back and did probably the most careful validation study I've seen. I hate to think how much they spent on the experiment. Just the experimental work alone to do this validation was really impressive. But you can see here. So this was a bushing under 4 channels of load, right? Radial, axial, conical, and torsional. And in this case, here's 4 different load cases that they've looked at. So this is the experimental fatigue life. This is the predicted fatigue life with our software. You can see that in every case, we were within a factor of 1.4 on fatigue life. In metal fatigue, they say if you can get better than a factor of 2, you're doing really good. We were able to get within a factor of 1.4 on life every time. And these are, if you look at the animations of these, which I don't have here, but if you look at the animations of these, they're very complex loading states, so it just again examples of things that people are doing with our software. Okay, so future directions. So some things to look for in the next year with our software. We're developing what I call a restart capability, which means that you will be able to right now when you run our software, what it tells you is how many repeats does it take to fail your part. In the future, you're going to have the ability to say, well, run this load case for 10,000 cycles, and then do a new thing. Right, it's really kind of an expansion of the multi-block feature that I've already showed you. We're going to be expanding that, and it'll be useful for doing things like residual life calculations. We're working on a stiffness loss capability where you would be able to model the progression of stiffness as a function of cycles in your part. We are looking at heat aging effects in elastomers, and finally load mapping and interpolation features. So these are all kind of future directions that you can expect to see in the next year or two coming out in the code. Okay, so I know that was quick, and we're up to 11:40. So I'm going to switch over now to a particular, let's see here, a particular example of our analysis. And this is a polyurethane mud pump piston seal. This is a project that we did with our partners at Vias, and I actually didn't do the modeling on this. Our analyst Mark Bauman and the Vias guys collaborated to pull this together. But I'm gonna just for the sake of continuity, I'm gonna talk about it. So here's a picture of the piston seal. Right, this is a component of a pump that is used to keep drilling fluids under high pressure. And I'll show you an animation of this later, so I won't say too much more than that. But here you go. So here's kind of the piston works. Right, it's inserted into this this bore, and then the fluid is kind of pressurized cyclically. And let's see here. So there's an installation right on the left-hand side. That's the animation that shows the installation. On the right-hand side, this is an animation that shows the operation. I'll run those through you again. So here's the installation, right? So you can see that there's a kind of an interference fit between the piston and the outside wall, and then that happens once, and then the actual fatigue duty cycle is this pressurization, right? That's going on, and you can see the seal kind of reacting to that pressurization. And ideally in the field, we would like to see 1,000 hours of life. This part operates at something like maybe 100-ish strokes per minute, and it's operating at temperatures that are up to 240 degrees Fahrenheit. And here's a picture of a failed seal with examples of kind of where cracks start to initiate. So the point of this is to predict the life, and then hopefully be able to use that model to improve the life of the piston seal. The basis for our analysis is the assumption that whenever you have rubber, if you get out a microscope, it is filled with microstructure, right? There are crack precursors already in that. Now, granted, they may be very small. Typically, they would range anywhere from maybe 2 microns up to 100 microns. But failure analysis is all about figuring out where and when do those small crack precursors grow up to a size where they become a problem. And so this, in our analysis, we've used these material properties. So there's a liner and the piston itself that are metallic things. Those are linear elastic. The seal is, of course, the interesting part. We've used an Ogden strain energy potential here, and we've plotted out the stress strain curves here. The data points are shown. We actually had, for this problem, we actually had limited experimental data. So, but we've done our best to fit a hyperelastic law. The blue curve shows the simple tension response of the material law. The green shows, for those who are familiar with using a hyperelastic law, is typical to do experiments in planar tension and biaxial tension. So the blue and the green and the red curves are the planar and the biaxial stress strain curves that are predicted from our model. And we could, here we haven't measured those, but we would certainly normally recommend measuring all 3 stress strain curves with our hyperelastic module. And I should also mention that the service temperature we're going to analyze is 170 degrees Fahrenheit. Now, we not only have to define stress strain properties, but we also have to define the crack growth properties. We can measure those using crack growth experiments, right? So here we're showing the typical crack growth rate curves that we would measure. Here we're only looking at cycle dependent, but if we wanted to, we could include, like I said before, creep crack growth properties. And this is a list of the properties. So we have an assumption, we have a determination experimentally of this crack precursor, or the flaw size. In this case, it's 3.8 times 10 to the minus 5 meters. Which is what? That's like 38 microns, which is pretty typical. Strength of the material TC, the power loss slope F naught 2.5. This is, I believe, this is a polyurethane that we're looking at. This is a slide that summarizes the boundary conditions on the model. So first of all, step 1 is fit the piston inside the liner. The operating pressure is 5,000 psi, and the question is how many cycles does it take, of that 5,000 psi in order to start, where is it going to start cracking? How many repeats of the 5,000 psi load is it going to take at 170 F? And again, just these animations. Now these animations are showing the strains and the stresses that are developing on the part. So you can see the corners, where you have corners, and in the model you're getting strain concentrations. So that's the insertion step. Here's the view with this is just von Mises stress plotted. Of course, we're not so much interested in stress. I mean, stresses and strain are interesting, but what we want at the end of the day is what's the impact on life. And so by taking these material properties and using these stress strain results with our analysis, we can find the fatigue life. I mentioned before we're using critical plane analysis, where for every point in the finite element model, we're going to do a search over every possible plane on which a crack might start. We're going to resolve the loads, the stresses to that specific plane. We're going to do a rain flow count on whatever history occurs on that plane, and then we're going to integrate our crack growth rate law using that information, and we'll just repeat that for every possible plane. And once we're done, we can see that, obviously the fatigue life depends on the orientation of the crack, and there will always be a particular orientation that results in the fastest rate of crack growth and the shortest amount of fatigue life, and that's what we predict as the orientation of the crack that nucleates. That's what we predict as the fatigue life for that element of the model. So this is just a picture of the workflow, right? We're going to take the strain history. We're going to do our critical plane search, right? Here's my crack, and I'm just scanning it through all of the possible orientations. For each orientation, I'm going to pull out a load history for that particular orientation. I'm going to do the rain flow counting. We're going to let's go ahead and we're going to get this to play. For each plane, we play the load history into the crack, and the crack grows. And then, like I said, we repeat this process for every element, and then we plot fatigue life on the part. And so this is the final result. You can see we're predicting the shortest life is basically kind of at this sort of intermediate place on the seal. Here you can see that the crack that after it's kind of initiated and torn through the seal, but you can see that, yeah, we got the location right. You can actually, and what's more interesting is you can actually do design optimization. So you can imagine that the shape of the insert here has an effect on the stresses and strains that are experienced, and you can ask the question, well, what shape should that be to get as much life as we can? In this case, we predicted a life of about 450 hours, and this was kind of an initial model. And then with the project, there was I believe it was a factor of 5 increase of fatigue life that was able to. I can't show the final model because that was a proprietary output from a project, but we were able to obtain a very substantial fatigue life improvement by doing a small number of iterations through the fatigue analysis. So that's just one example. We've also done analyses on blowout preventer seals. We've done O-rings. The workflow is very simple to use and powerful as well. If there's a very large palette of different effects that you can include depending on your application. So with that, I guess I'm gonna just maybe kind of end with, I guess maybe I'll end with an announcement that we're coming to Houston at the end of July. We're going to be giving a class, and we will be emailing a link to everybody who's come where you can sign up for the class. But it'll be a 3-day event. The first day is going to be presented by the Vias people, Arendam, and it'll be focused on FEA of elastomers, right? Setting up your model for rubber, and then the last 2 days we'll be using Endurica to solve these kind of problems. So if you want to come and get hands-on experience using our tools, there's an opportunity to do that coming up here in about a month. And so just watch your email inbox. I guess with that, I'll open it up for questions, comments.
Hi, this is Arindam here. Thank you, Will, for the nice presentation. I'm hoping some interesting questions to come up. Some of the things we would also like to know from more practical experience that you guys are dealing with, and what are your pain points. And as Will mentioned, so the event will be at our Vias office here in Houston at Energy Corridor. And we will send a follow-up email from this webinar, and we'll include the details of the training there. So if you would like to attend that, please take a look at our follow-up email. Thank you.
So if you've got a question, use the chat feature. I think everybody's probably muted, but so yeah, if you've got any questions, go ahead and use the
so if you have a question, please write it at the chat window, and we'll be able to see it, and we'll read it out for everyone.
So let's see, we've got one coming in here. If the rubber part loading is only compressive, is there a fatigue concern? Excellent question. So one of the well, you can imagine that if you were to take a crack and put it in a cube of rubber, and then drop it to the bottom of the ocean where you have lots of hydrostatic compression. No matter how that crack is oriented, it would always be closed. And if it's a true hydrostatic compression, there wouldn't be any shear. So yeah, in that particular case, there would be infinite life. Now, what happens in cases where you don't have perfect hydrostatic compression is, in compression you do have crack closure, but you also can have shearing of the crack, right? And Endurica's software makes a specific account on a per plane basis of when and where crack closure is happening. If you do have crack closure, it does take account of any shearing action on the plane. So yeah, we do account for that. You can have fatigue failures in compression, absolutely. But in compression, and in fact in compression, sometimes people ask me whether if you could just use maybe like a max principal stress to predict fatigue failure. And if you have very simple tension loading or very simple shear loading, sometimes you can. One of the cases where using max principal stress as a fatigue predictor breaks down is when you have compression because of the crack closure effects. But that's one of the reasons why we need critical plane analysis, is because we can be very specific about crack closure, but we can still account for the finite life that comes from the shearing actions. What is required to prepare the elastomer sample for you to perform the material properties test? So with our testing service, the standard way to do that is to send us compression molded tensile pads, right? If you're making rubber compounds, or if you have a supplier, it's a fairly common standard is to mold samples of the rubber in sheets that are 6 inches by 6 inches by maybe 1/10 of an inch, or 150 millimeters by 150 millimeters. So that would be our standard go-to, is just send us tensile pads. Sometimes if you're working with a part that's big enough, it is possible to sort of slice test samples out of a part. If you have a case like that, talk to us and we'll figure it out. Yeah, but so you can send us tensile pads of rubber. Another question, is this presentation available for our use? We haven't talked about that, so we'll talk to Aaron. I'm happy to make it available, and so I think we can find a way to maybe he's on the website or something.
Yeah. Well, I just responded on text as well. So yes, we will make this available, and also we will put a link to the recording of the presentation.
Great.
And we'll, in the follow-up email, we'll mention everything. Thank you for asking.
Right. So that's I'm not seeing any more questions here. So again, thank you for your time. Thank you for your interest. Like I said, we've by now Endurica has been used on more elastomer durability problems than any other system that I know of. I think you'd be hard pressed to find one that's been applied more widely. We've people in the automotive sector are using it, the oil and gas sector, defense, and so we definitely proud of it, and looking to help whoever wants to use it.
And also one more thing I want to mention, that apart from supporting on your regular project, if there is a need, if you are looking into more R&D sort of thing, I mean, trying to analyze a problem that's probably troubling you for long. So we also work towards those kind of R&D project, and we take your problem and try to give a solution working with you hand in hand. So if you have those kind of queries, please let us know. We'll be more than happy to have a conversation. Yeah, there's one more question. Endurica, does it work with ANSYS as well? So Endurica in general, it's a software neutral solution, so it should work with any other finite element software.
That's correct. So if you look at the ANSYS, or excuse me, if you look at the Endurica CL user base, we actually we currently have customers who are using 3 finite element codes. Abacus is obviously that was where we started, and that's our biggest. ANSYS, we definitely have people using the ANSYS platform, and we fully support that. And then we also have customers who are coming and using Endurica from Mark, so yeah, it's really a code neutral kind of solution. And if you'd like to see what the workflow looks like, you can go to our YouTube channel, and there's actually demos on YouTube that show what it looks like to use the software. So I'd encourage you to look there. So if you just go to YouTube and type Endurica, and you'll find our demos.
Yeah, we are here for a few more minutes. No problem. So if you have any question, please let us know.
All right.
Well, I think we'll just keep it open just in case if somebody has something to ask for. I would like to, whoever is still there, I would like to thank them again for attending this webinar, and hope to have more queries from you guys, and we'll take it from there. Thank you. And thank you, Will.
Yeah.
Yeah, I'm closing the meeting now. So,
Thank you.
yep, thank you.